Hello everyone, welcome to my YouTube channel. My name is Vasundhara from Sri Venkateshwara College of Engineering and currently pursuing my data science engineering. So today we are going to look into the topic which is from mathematics, and I have chosen the topic which is known as vector calculus. Introduction to vector calculus. Vector calculus is a branch of mathematics that deals with vector fields and functions. It involves the study of differentiation and integration of vector field. Vector calculus is essential in various scientific and engineering fields such as physics and computer graphics. To define a vector in a simple form, it can be known as standard notation for three dimensions such as XYZ components. Vectors in Cartesian coordinate systems. Vectors in Cartesian coordinate systems are represented by the magnitude and direction. In 3D space, vectors can be described using coordinates axes x, y, and z. Vector components in Cartesian systems can be added, subtracted component-wise. Vector operations. Vector addition is done by adding corresponding compounds of two vectors. Scalar multiplication involves multiplying a vector by a scalar to change its magnitude. Dot product and cross products are two important vector operations used in vector calculus. Gradient of a scalar field. The gradient of a scalar field is a vector that points in the direction of maximum change of the scalar field. It is calculated using partial derivatives of the scalar field with respect to each coordinate's directions. The gradient is perpendicular to the level surface of the scalar. Divergence of the vector field. The divergence of a vector field measures the rate at which the field is expanding at the given point. It is calculated by taking the dot product of the vector field with the del operator. Divergence is a scalar quantity and can be positive, negative, or zero at a point. Curl of the vector field. The curl of the vector field measures the rotation or circulation of the field at the given point. It is calculated by taking the cross product of the vector field with the del operators. Curl is a vector quantity and points in the direction of maximum circulation. Line integrals. Line integrals are used to calculate the total value of the vector field along a curve. They involve integrating the dot product of the vector field and the tangent vector to the curve. Line integrals can be evaluated using parameterization of a curve. Green's theorem. Green's theorem relates a line integral along a closed curve to the double integral over the region enclosed by the curve. It established a connection between line integrals and surface integrals. Green's theorem is useful in calculating circulation and flux of vector fields. Surface integrals. Surface integrals are used to calculate the flux of the vector field through a surface. They involve integrating the dot product of the vector field and a surface normal vector. Surface integrals can be evaluated using parameterization of the surface. Gauss diversion theorem. Gauss diversion theorem relates a surface integral of a vector field to the volume integral of the diversion of the field. It establishes a connection between surface integrals and volume integrals. Gauss theorem is a fundamental result in vector calculus with application in physics and engineering. Stokes theorem. Stokes theorem relates a line integral of the vector field along a closed curve to a surface integral of the curve of the field over the surface enclosed by the curve. It establishes a connection between line integrals and surface integrals. Stokes theorem is crucial in understanding the circulation of vector fields. Applications of vector calculus in physics. Vector calculus is used in physics to describe various physical phenomena such as fluid flow, electromagnetism, and gravitational fields. Maxwell equations which govern electromagnetism are formulated using vector calculus concept. The Navier-Stokes equations for fluid dynamics are also expressed in terms of vector fields. Applications of vector calculus in engineering. Vector calculus plays a scientific role in engineering disciplines such as structural analysis, fluid mechanics, and signal processing. Finite element analysis and fluid dynamics rely on vector calculus for modeling and simulation. Control systems engineering utilize vector calculus for system analysis and design. Numerical methods in vector calculus. Numerical methods such as finite differences, finite elements, and finite volumes are used to approximate solution to vector calculus problems. These methods are essential when analytical solutions are not flexible or expensive. Numerical stimulation in vector calculus enable to study the complex systems and behaviors. Conclusion. Vector calculus is a powerful mathematical tool that underpins many areas of science and engineering. Understanding vector operations, gradient, divergence, curls, and integral theorem is crucial for solving real-world problems. Mastery of vector calculus provides a deeper insight into the behavior of vector fields and their applications.